Unlocking the potential of weather and climate analytics. How one company is building a constellation of satellites to empower communities to prepare for extreme weather. Using the latest weather technology and artificial intelligence to track hurricanes. Gathering data from the surface to high in the storm. The new dual sod. This is NTWC Live.
Good morning, everybody. Welcome to NTWC Live. It's the 18th day of October of 2023. Good to have you all along today. Great program for you today. We're going to be talking about cool stuff with understanding what's happening within the hurricanes with satellites, all kinds. It's going to be a great show. You're going to like it. We'll get to it in just a second. Bill Reed is here. Hurricane Hal is here. And our guests are here. Michael Isles, Kim Keisty are here. Joshua Wadler also joining us this morning. But I want to thank our sponsors. First, those who make this program a reality each week, because we couldn't do it without them. And it's important we thank them right off the top. And that's USAA. My goodness, USAA, a big part of the Storm Science Network, a big part of the National Tropical Weather Conference, and by virtue of that, NTWC Live. So thanks to USAA for all you do. South Padre Island Convention and Visitors Bureau, every year we're live in April at South Padre Island. We'll be there April 2024 at the Courtyard Marriott Hotel. Once again, if you've been there the last year or two, you know about the hotel, you know how great it is on the beach. We encourage you to come join us. All the stuff we're doing here through this webcast, a lot of it we do live in person in April, so thank you for that. The Weather Company, providing graphic systems for television stations around the world, including mine, Alex's, and a bunch of others. And finally, Weatherboy, relatively late add to our programs, and we really appreciate what they've done because they help bring college students to the National Tropical Weather Conference, and we appreciate that. So thanks to Weatherboy for being part of this. All right, a lot to talk about today. Bill and Hal, I'll start with Bill. We've got some great guests today. I think it's going to be a fascinating program, and the hour's going to fly by. So good morning. We'll start with Bill. Hey, Bill.
Good morning. Yes, we've got a busy calendar here today, and it's a lot of stuff that I'm eager to learn about that I really haven't been familiar with in my luxurious retired state. So I'll get right off and introduce two of our guests and let Hal introduce the third. First off, I want to introduce Mike Isles. He is now the General Manager of Weather and Earth Intelligence for Spire Global. He has 4 decades of technical experience in meteorology and climate. And I think I've interacted with Mike through each of those 4 iterations. Most memorably, and most of the audience would probably be familiar with, is creation of radar scope at WDT when he was running that company in there. We also have Joe Cione was advertised as one of our guests today, but he's flying what should become Tropical Storm Tammy sometime in the near future. So we now have Joshua Wadler, who I'm assuming works with Joe. And Joshua's research interests broadly cover tropical cyclone structure and intensity change, and focusing on new sampling techniques and platforms such as the small uncrewed aircraft systems that we're now experimenting with in the recon business. So those are 2 guests there. Hal, how about if you introduce Kim?
Yeah, y'all are going to be so excited to meet our third guest today, Kim Keisty. Really exciting stuff that he's done. For more than 30 years, he's worked in the global navigation satellite system industry, developing receiver modules from 1992 to 1999, working with radiosondes and dropsondes. And then really since then, since 1999, they've been working with an entity called U-Blocks. They've developed receiver modules with that, and they've really grown the business, working a lot from Finland. From 2012 to 2019, they grew the U-Blocks R&D team in Finland from 20 to about 100 people, and now they already have 150 people working in Finland. Kim, so great to have you on NTWC Live today.
Thanks.
Okay, I think I'll start with Mike. You're now out in Colorado with Spire Global. I don't think most of us know much about your company and the exciting innovations you're bringing forward to the community. How about if you fill us in on that?
Well, absolutely. I will share some slides. But before I do that, I just want to say Spire's been around for about a decade now, 11 years actually, and one of the largest satellite constellations. We've launched over 150 satellites as a business. And we collect RO data. Well, I'll talk about that a little bit here too, but did an IPO in 2 years ago or so, and now are listed on the New York Stock Exchange, about 400 employees. So it's an exciting company. I just joined them in January of this year. They brought me on to help them think through their weather strategy and their what we call Earth intelligence, which is from space we can sense things like soil moisture and ocean winds and those kind of things. But if it's okay, I'll share I've got like 5 slides or 6 slides here, and I can walk through that, and if that works for you all. Let me figure that out again here. There we go. So, I want to start with, this fundamentally, space-based data is fundamentally changing the weather industry, and the amount of data available and the vantage point from space actually creates a huge opportunity for the whole industry, the whole enterprise, not just the private side, but the enterprise. And Spire is on the leading edge of that. We've really, as a business, let me go into presentation mode if that will help. Does that look okay, everybody? We see everything?
Good.
Okay. So Spire is the only private weather company with a satellite constellation. We have over 100 satellites in space today. We've launched over 150. The reality is these satellites only last 3 to 5 years, so we have to constantly replenish them with better satellites and more satellites. But what's exciting is that these nano satellites, and the picture here is what they look like. They're only the size that box is only about the size of, say, a wine bottle or a box that a wine bottle sits in. They're not very big, so we call them nano satellites. But from those, having 100 of them in space, we can actually collect up to 14,000 times per day, radio occultation, which basically is profiles of temperature and humidity throughout the atmosphere. And this graphic on the bottom here shows you what we collect in 24 hours. So think of 14,000 radio sounds going up every day, and that's a great advantage to us to use for simulating data into models and doing other unique things with it. And so we have a growing team of 20 meteorologists, PhD meteorologists, and a whole bunch of other scientists and engineers. And we're doing some really exciting stuff with our own unique data. In addition to selling it to the ECMWF, National Weather Service, and other organizations that put our RO data into their models, making them better. So it's not just ourselves, but the forecast you see from ECMWF and GFS include our RO data. Let's see, there we go. I wanted to talk a little bit about how this actually works, because it's amazing, the process. And so there's all these GNSS satellites, which are just GPS satellites, right? So we're all used to looking on our phone and we can tell where we're at, even if we don't have cell coverage, because there's GPS satellites out there, and they're constantly transmitting. And we have these 100 satellites floating around space at about 300 to 400 kilometers altitude. And they can see directly to the GPS satellites, and they also can see as it's bent through the atmosphere. So when it's bent through the atmosphere, we can get temperature and humidity profiles. When it goes through space, or the top part of the atmosphere, the ionosphere, we can see space weather information. And then when it bounces off the ground, we can get soil moisture, we can get ocean winds, and we can get sea ice from it, and other things, including other things. So it's really exciting that we have also all this data where we're just listening satellites. We're not transmitting satellites. We're just listening to the GPS data, and then we're doing machine learning and analytics to understand what information we get. And we're doing much more. In 2024, we're launching hyperspectral microwave sounders, which is even more exciting, but I won't go into that today. One of the things we do is we run our own global forecast model. And what's amazing to me is a relatively small team in Boulder, Colorado has built a global model. And now I'm not going to spend too much time looking at this, but our forecasts from our global model are actually better than the GFS model on bulk statistics, everything, especially over the oceans, because we have a lot of extra data over the oceans than, say, the GFS model does. To be fair, we're not quite as good as ECMWF though, and we do statistics. But the gray bars here are GFS. The green bars are ours. Smaller is better. Just shows you that. And then the other bars are how we take and use AI and machine learning to get even better forecasts at specific points. So, but the point, I think the more important point here is we can use our own data and create better forecasts. But ultimately, just having another forecast in the world doesn't create significant value to our customers. So we have to do a lot more. We have to think through how do we turn this into something that's really useful for our customers. And so now we're running very high resolution models, 1 kilometer, 3 kilometer over Europe, over Texas, basically we're running over Florida, and creating significant value for our customers by very specific data. Again, we're using our RO data, we're using our soil moisture data, we're using all the other weather data that's available commonly to all models, but we have a bunch of proprietary data. And it gives us an opportunity to, for example, one of our customers in Florida, a big utility there, loves the forecast because of the, we can help them define on a day-to-day basis, our storm's going to form in the west and move east, or storm in the east and move west. Where will they be most intense? So they can stage crews, for example, in advance of storms of the day. The other things are commodity traders. We have a lot of commodity trader customers over Europe and the United States that are really excited to see this data because it really helps them understand where wind power is generated, where electrical demand is going to be for the day or for the next few days, those kinds of things. But then we've really worked on how do you take, if you have better forecasts and you have soil moisture data and you have other kinds of data that nobody else has, what do you do with it? And so we created this product called Deep Vision. And I just want to give you a sense of it. It's a complete system that takes our forecast, takes all the government information that's available, all of the National Weather Service watch the warnings in Europe and other places. But we really focused on, we can do forecasts for points, both static and moving. You can give us your 10,000 trucks and we'll give you a forecast for all their routes. We can do aerial custom polygon forecasts. We can do threshold alerting based on our forecasts. We have dashboards like you can see here. And then we built a weather risk communication team. So senior meteorologists behind the scenes that help us think through, use our forecast, use our high resolution models to help our customers think through some things. So again, for example, a utility in Florida, allowing them to have access to meteorologists to help their meteorologists think through events. Their meteorologists are too busy to deal with, especially during hurricanes or tropical season. Now we're kind of winding down the daily kinds of forecasts they need to deal with, but still hurricane season is obviously upon us, and our team helps their team basically, but we also give them all the tools that you're seeing here, for example. And then, if you step back and you think about the global supply, since we're a global company and one of our values is global, actually, to think through how do we help companies that are moving assets all over the world. So supply chain, logistics, those kind of things. We have a pretty big maritime. Not only do our satellites sense the things I talked about, we actually track every single ship in the world. And so we know, including dark ships that try to hide themselves, those kind of things. I'm not focusing on that today, but that's the other thing we do with our satellites. And the ability to combine that with our data and provide information. So we can do trucks, we can do railway, we can do ships, and we can do aviation. So we can track parts from one part of the world to the other part of the world, help with risks, help with ETA, help with minimizing emissions from, so helping companies go green and deal with climate change, both, all in one simple solution with meteorologists behind the scenes. But a lot of data goes into that, a lot of proprietary data goes into that. And that's the main message I want to get by today. I didn't really want to spend a lot of time just talking about stuff like this, but love to answer any questions or discuss more about what we do.
That's a lot of information there, Mike. That's an amazing company you're working for there. Who launches your satellites?
We use mainly SpaceX. We have used other companies too, but we put like as many as 9 or 10 on one rocket that goes up, and it's amazing the process. They launch And when they get to the right spot in the height and altitude or whatever, basically they just get sprung out from the there's a big spring that pushes them out, and they're on their own. We have no propulsion in those satellites. They just the solar panels open up and they're kind of like wings, so we can kind of control a little bit with that. But there's no propulsion at all in those satellites. And like I said, they live 3 to 5 years. We have 30 plus ground stations all over the world. As they pass over them, we can collect data from them. So we basically get global coverage from our 100 satellites that about a 15-minute update globally, basically.
That's incredible. Do you have them in different orbiting configurations to get that coverage?
Yeah, they're all in different. When we launch in certain ways, and they get sprung out of a satellite, they get different space, or out of a rocket, they get put in different places in orbit. So we have this sort of, if you imagine 100 satellites all over the globe going in different trajectories and different, but most of them are about the same altitude, 300 to 400 kilometers above Earth.
Interesting. And even after with no fuel, I guess that's one of the limitations why 3 to 5 years is about it for them. And
right. Yeah.
As small as they stay up there for quite a long time before they get pulled back into the atmosphere, right?
Yeah, they do. I mean, and it's kind of funny. We've been talking about how we're trying to extend the life of some of them, and we can kind of turn them off. We call it putting it into Superman mode. So think if they're going normally sort of vertically, they have kind of a certain drag coefficient, but if you turn them so they're sort of facing where they're going, their wings are out like Superman, it has less drag, so they might last an extra year, for example, but we can't really use them at that time, but we can kind of store them in space, if you will, for a longer period of time. So we're doing some of that right now to try to think through where we want to be. If everything fell out of the sky at the same time, it would not be good. And so we're working through some of those scenarios right now with the business.
That's incredible. Thinking on your modeling, with that 1 to 3 kilometer resolution, have you had much success on tropical cyclogenesis?
We haven't really. We just launched it recently, and we've done it mainly over Europe and over central United States. So we haven't really focused on that. We do believe, though, the RO data we've shown, and I didn't show it today, but we've shown that in our global model that we do a really good job at some of the tropical cyclogenesis and other things because of that special data that we have in the oceans that other people don't have. So we think our model is at least comparable and slightly better than some other global models for producing hurricane tracks and hurricane intensity forecasts and obviously in the early stages of tropical cyclones.
Yeah, most of the people I know that are researchers in the modeling world think that's that 1 to 3 kilometer sweet spot is where they need to be to have some success at the genesis part of the problem.
Yeah, it's an interesting place we want to be. When you get down to 1 to 3 kilometer range, then you can, you're actually, and you do a really good job of data assimilation. You can really kick off the models in a realistic manner. And that's the other part. We mentioned we have 20 PhDs here. The data assimilation team that we have, they do amazing things with the data. We've taken many scientists from NOAA and FSL, and those labs have come to our office here in Boulder and work with us now, and we partner with some of those organizations too. And the things that we do to kick off models with excellent resolution and we start off the model with the storms in the right place and the clouds in the right place, and that way you have a hot start, if you will, and you can create really, really exciting forecasts even in the first 1, 2, 3 hours, which many other models, everything rains out and then restart again, for example.
Right. Yeah, I've been very intrigued by where we're going with the resolution on that. I can see Hal there just chomping at the bit to eat the microphone. So far away, Hal.
Michael, really fascinating presentation this morning. I had a question for you. Where's that interface in your system between modeling and what's going on in the ground? Because you do so much on planning and help people really track and forecast logistics. Let's say your satellites are predicting a massive storm system in Europe and someone's shipping something across Europe. Do you also look at, say, river heights, and will a river cross over a road and shut down a transportation route? Or are you more focused on really what's going to be happening in the atmosphere?
I will say that with our data we can do soil moisture and flood mapping. We aren't there yet, but that's definitely a vision of ours too, is to get there, because we can use our satellites to do very interesting stuff and do some flood monitoring at least. We can't really do flood prediction yet with that, but we can definitely do flood monitoring. So absolutely, we don't do it today, but we're definitely running hard towards that, because we think it's all that we want to handle all the environmental impacts on on a shipment or on a truck or a train or whatever. That's the ultimate goal.
Michael, also, when you mentioned improved accuracy of your system, I'm curious about feedback loops you might have with AI or machine learning. For example, let's say a forecast, the conventional forecast does not have rain in it, but all of a sudden a slight rain shower pops up. Can your system really do a quick feedback loop and say, hey, let's edit today's forecast, maybe quicker than conventional methods?
We are, I'd say not quite yet, but with the high resolution models, we're running them every hour, right? So you do get that, the her kind of thought process for sure. I think the other part of it, though, we do a lot of post-processing AI ML kinds of things that really create probabilistic forecasts and using other tools to create better forecasts. We haven't gone into correcting forecasts yet. In the future, as we diverge from reality, for example, but that's a natural place for all of us to go in the industry, I think.
Michael, I also wanted to ask, your improved forecast accuracy over models like the GFS. Do you think part of that has to do with your exceptional high resolution of your work?
Well, when we compare accuracy to accuracy, GFS, we're comparing to our global model, which has the same resolution as GFS, and so in that case, it's because we have RO data and we run the same model as GFS, the model core. We just have better data going into it. Basically, we have more data going into it. The high resolution models do even far better. Honestly, we haven't done that direct comparison over the same area, but you can just see examples of pictures or images of comparing GFS, or what we call soft D, which is our global model, and our own high resolution models, and the amount of detail and the amount of information you get from the high resolution models is far superior.
Thanks, Michael. Tim, I wanted to pass it over to you. Do you have any questions, or have any questions come in from online?
Yeah, we're getting quite a few, and let me just ask one. The first one is, where's the model data available? Is it by subscription only, or is it available to the general public? And is it specific regions, or how do we get a hold of that?
So if you're a WeatherBell subscriber, it's part of their standard. You pay something. I'm not sure how much you pay to do that, but if you're a WeatherBell user, you can get the data there. Otherwise, we do sell it as a subscription, either through an API or in a few other ways that we can get data to people. But WeatherBell is probably the easiest way to get access to it.
That's good to know. And then Casper's asking about with no propulsion, is there any way to control the re-entry of these as they start to fall back? Is there any way to control that?
I don't think so. I think they just burn up and they're gone. I'm not a satellite expert that way, but as I understand, they just kind of burn up when they get to a certain place, and we do everything we can to control them, but when it's time to go, it's time to go, basically, and they just burn up.
This is fascinating, and there's many more questions, but I know we've got more guests to get to. So let me go back to Bill, and we'll move forward. And great stuff, guys. Great. Thanks, Mike.
Yeah.
Thank you.
If we manage to keep this within an hour, it's a miracle. So thanks again, Mike. I hope you can hang around, and maybe we'll have more questions for you as we go along. I want to bring Joshua Wadler now. Welcome to the show, Joshua, and on short notice, thank you for covering for Joe. How about telling us what it is you do?
Hi, everybody. Well, nice to meet you. I'm Dr. Josh Wadler. I'm an assistant professor of meteorology at Embry-Riddle Aeronautical University in Daytona Beach. So I work very closely with Dr. Joe Cione and NOAA with new and emerging technologies. And so a lot of my research is in how can we improve the measurements that we make, and what are better measurements to take in hurricanes so that we can better understand how they intensify and how can we better predict them.
So I understand you are working on the the uncrewed aircraft that are launched from the P3. Is that correct?
Yeah, so it's a really exciting project to work with the uncrewed aircraft. So we're working with two different type of uncrewed aircraft currently. The Altius 600 built by Anduril, which is about a 27-pound aircraft, and then a S0 built by Black Swift Technologies, which is actually only a 3-pound aircraft. And so Joe Sion, who was supposed to be here, is actively deploying into potentially launching both of those systems into the new storm.
Great, and they're still considered experimental, right? They're not really ready for operational use and mass production, I assume.
Yeah, so we're constantly testing. We're seeing what are the benefits and things that we can improve on the instrumentation. So, for example, are the measurements reliable? Will the airplane fly consistently? And things that we need to improve in order to make it a standard part of practice. One other thing that we're always working on is communication range. And so imagine this is like a 3-pound drone, very small aircraft, and it has to transmit information to the Hurricane Hunter, the P3, that could be over 100 miles away. And so that's no easy feat. And the engineers that work on this are really, really smart and able to make this happen.
And what's the what are the data you're collecting with this, and the altitudes that you're trying to sample when you launch one of these?
Yeah, so we're collecting standard meteorological data: pressure, temperature, humidity, and winds. So the aircraft is flying horizontally. Normally, the P3 flies at about 8,000 feet, or between 8 and 10,000 feet. It cannot fly above that because of icing concerns, and it can't fly below that because of you're way too close to the ocean. And so the drones fly really low. Typically, we start them at about 5,000 feet, but they go as low as we're hoping to fly like 50 feet in a hurricane for extended periods of time. Of course, if the waves allow that to happen. But yeah, they fly really low. Eventually, they hit the ocean. We do not recover them. So the large drone can fly upwards of 4 hours, and the small drone can fly upwards of 1.5 hours.
Oh wow! Are they electric or motors that drive them?
Yeah, they're currently all electric. So they're battery operated, both that we use. And so they are released from the Hurricane Hunter in a tube, and they're in a cylinder. And as soon as they're released, their wings come out and they start flying. And it's really engineering marvel how they get it to work. Yeah,
and back in the long time ago when I was flying, there was a significant loss of sensor in the launch from the aircraft. I know that we've mostly cured that problem with the dropsondes, but do you lose any of the aircraft in the launch procedure out of the airplane because of the forces involved?
That's definitely a big part of the research. The forces that the instruments experience are immense, as you mentioned. One thing that we do before launching any instrument is a clear air test. So basically, we launch a non-electronic version or a model where we try to make sure that the instrument can survive being launched out of the plane. So that's optimized before we even put in the actual instrumentation. And there is a back and forth. Sometimes it doesn't work right away, and it needs to be improved. Kim Casey, who's on this call, is also experimenting with an atmospheric profiler called a StreamSon, and they've done a remarkable job also of improving their technology in response to those very strong forces that you experience being launched out of the Hurricane Hunter.
Great. Well, we're getting to Kim after the midpoint here. Hal,
Sure.
You've got a question on your mind.
Yeah, Joshua, I wanted to ask, with the potential of drones collecting data from 5,000 feet all the way down to, say, 50 feet, would you picture them more flying transects at a consistent elevation, or would there be times where they might actually just drop straight down vertically and kind of get a vertical profile in one section?
So we do have atmospheric profiles that go vertically. So those are dropsondes. So we release them from the P3, and they take about 2 minutes to fall straight to the sea surface. And so we do have atmospheric profilers. So typically we fly the drones horizontally over some time, just so we get the most value of the measurements, because they can last for a long time. In terms of transects, what we've done so far is fly them around the eye wall. So we had a big success in Hurricane Ian with the Altius 600, flying for over an hour and a half in the eye wall of Hurricane Ian of last year. It actually measured 215 mile an hour winds at about 2,100 feet altitude. And so these drones are strong, they're sturdy, and they can withstand those winds. And so if you're flying around the eye wall, imagine now we can take measurements and know what the winds are at all azimuths around the storm at a given altitude. And that's just something we did not have the capability of before.
Thanks, Joshua. It sounds like this technology is incredibly durable.
Yeah, we try. Certainly that's the idea. You don't know if it's going to survive until you launch it into a storm. And the idea usually is to crawl, walk, run, and to take baby steps. But the first time we launched the Altia 600 was into Ian, as it was near Category 5, and wasn't exactly following that motto, but it worked. So we're very happy about that.
Thanks, Joshua.
How do you keep a small aircraft like that stable in the turbulence of the eye wall? Such, with the airplanes, they try to keep the attitude level and let it go up and down with the turbulence. What do you do with these?
So it does bounce up and down. Obviously, that one's 27 pounds, so there's only so much resistance you can have. So there's a very advanced autopilot that enables it to correct for altitude. But so in terms of turbulence, the hurricanes can survive actually quite well, because what matters to the aircraft is the difference in forcing on both wings. And so as long as the forcing is the same on both wings, the aircraft has, it's easier to survive. And so the scales of the turbulence in hurricanes are on the order of about 2 kilometers or just over a mile or so. So it's very unlikely that the forcing on both wings would be asymmetrical.
Yep, and your autopilot doesn't get motion sick.
No. Definitely some people do on the aircraft. I've been fortunate so far. I haven't lost my stomach on an aircraft, but a lot of people do.
It's good time to take a break. Good time to take a break. Fascinating stuff, and we got more coming up after the break. But let's take a moment, thank our sponsors who are part of this program each week, and then we'll get on with more of this stuff. This is great stuff. USAA, thank you for what you do. South Padre Island Convention and Visitors Bureau, an important part of this program, week in and week out, and we'll be live there in April 2024 in South Padre Island. The Weather Company and Weather Boy, all part of NTWC Live. Okay, we'll get back to this discussion on all this great new technology, all the great things happening and trying to analyze these hurricanes and tropical storms and day-to-day weather. But first, let's get a look at what's going on today in the tropics. So, Bill, bring us up to speed. We're mid-October and we're not done yet, at least in parts of the world.
Okay, I apologize in advance. This old guy is in old technology for what I'm showing you compared to what's out there, I'm sure. But it's readily available at low cost on the internet, so that's what we get. Latest satellite imagery, you can see the system has gotten a lot more tropical storm looking than it has the last several days that NHC has been monitoring it. And it looks like it's nearing that point where it might become a storm. It would not surprise me if it hasn't become a storm by this afternoon, that NHC will have to go up with a potential tropical cyclone and start issuing advisories on the islands here. A lot of them are mountainous, and even if the surface winds aren't quite there yet, the winds aloft, not very far aloft, will do quite a bit of havoc up in the mountains there, and that's one of the reasons they went to the PTCs for that. Elsewhere, we got our frontal boundary down here interacting with a whole bunch of moisture in the Caribbean. It's not going to develop into anything tropical, at least as far as I could tell. Make sure they haven't started issuing advisories yet on it. Nope, they haven't. Again, it's at the light. It's going to develop in their minds, and I think that's a fairly easy statement to agree with. The guidance, the latest track guidance in there now shows most models do bring it into the northeastern Caribbean islands before recurving it out into the open Atlantic, and the intensity models. They've been all over the map. This current set of guidance are not as rambunctious as some of the others. Most bets are it would stay as a tropical storm, but as we all know, before something's actually developed, there's a lot of error in this type of forecast. The ensemble models are fairly striking. Most striking thing I see between the ECMWF and GFS is the GFS is forecasting a stronger storm in the model members than is the ECMWF at this point in time. Out in the Eastern Pacific, we have Tropical Storm Norma, unless it's become a hurricane. I'll pop that up here in just a minute. We also have a disturbance that will be coming off of Central America and slowly developing. Maybe by the weekend, we'll have another storm to deal with in the Eastern Pacific, and this at a lower latitude and maybe more interesting further south in Mexico. See if we got a new one. Still a tropical storm. Nothing's really changed from the earlier forecast except a little slower. See, Tim, you can make it out to your place in Cabo and maybe report live from the storm next Wednesday to our show. It is forecasted to move very slowly north, and there's a big difference at the end here. I'll show you in the model solutions. Briefly attaining a major hurricane status over the next day or so. Again, there's a fair amount of uncertainty in both parts of the forecast. It's a large system at the present time, large area of convection in there, so the impacts could be more widespread than some of the more traditional, smaller East Pac storms that we deal with. The track guidance is pretty consistent for a day, 2 days, and maybe even into 3, and then it gets lost because the steering currents go bad. Plus, the different model solutions that they're based on have very different ideas of where it's going to go. Intensity-wise, there's a strong signal for rapid intensification here over the next 24 hours. Then leveling off and slowly decreasing as it gets into more hostile conditions. And as you can see, as you get past, this is a 5-day ensemble there, as you get past day 3, into day 3 and 4 and 5, there's a widespread in the solutions on there, hence the uncertainty of the ultimate outcome. That will become clearer in 2 or 3 days. So, Hal, I'm going to turn it over to you and let you start the discussion with Kim.
Yeah, that sounds great, Bill. Thank you so much for the tropical weather update there. Kim, so excited to have you on the broadcast today. You're coming from all the way in Finland. I don't know if we've had anyone from Scandinavia join us for the National Tropical Weather Conference before, but really glad you could be here. I really wanted to hear from you. You know, you have more than 30 years experience working with this type of technology where we're doing remote sensing, GPS, drop zones. Really, how have you seen the technology change over time, and where do you think we are today?
Thanks. Yeah, I've been doing radio zones and GNSS like for 30 years. And when I started, the only wind finding method was like Omega and LoRaWAN-C back in the early 90s. And then when GPS came along in the mid 90s, that changed the world dramatically for radio zones and drop zones in terms of accuracy for the winds. And we have now been developing a couple of years, thanks to Joe and Josh helping the National Hurricane Research Center. So this is our latest development, a stream sonde, which can be used either as a radio sonde or a drop sonde. And Josh mentioned that the smallest drone is about 3 pounds. This is half an ounce, so 14 grams. So, and the small weight enables it to freely flow with the winds and measure differently than the current drop zones. So we have a little bit of different angle to it. But I have a couple of slides I could share you if you don't mind about the technology. Let me see if I can pull it up. Share. And if I go into presentation mode. Do you see it now? No.
Yes.
Yeah, very clear.
Oh, I see it on my screen as a small, but okay, so you see a big screen.
Yes, we do.
Okay, perfect. Yeah, so Skyfora, we're founded 2019. I joined 2020, and I'm responsible for all the hardware and instrument development. So the weather instruments, the sondes mainly today. But we also do these AI-based weather forecasts. We have a product called Tropical Storm Tracker, which Bill could have shown us as one example of where how the storms are evolving, but that's not the topic of today. I'll be talking about the instrument side. So first of all, the stream sound is ultralight, 14 or half an ounce or 32. The bigger one has a bigger battery because it needs to survive the radio sound conditions, and the mission is longer and the temperatures are really bad in terms of the battery. So we have to put a bigger in the radio sound use. But it works as any sound in the 400 megahertz mid band, depending on the battery, 2 to 4 hour operation time. We have also a rechargeable version, which is good if you use it from drones or these UAVs. But the ultralight weight makes that the terminal freefall velocity is very low, so it's less than half of a traditional drop zone. So it measures the free flight takes double in time, so you have more data points coming down. We have the normal pressure, temperature, humidity sensors like all other zones, but we also have, I'll talk about it a little bit, custom-built, very high accurate GNSS, and then the motion sensors, 3D gyro accelerometer, magnetometer. We also have an air quality sensor capable of measuring ozone and NO2, and then ambient light sensors. Those, the two last ones are not necessarily needed for the drop zone, but the motion sensors do give good insight of what's going on physically with the sound as it's coming down. From operations point of view, it can be deployed with balloons like radio sounds, from airplanes like the P3 and UAVs. And due to the lightweight, we require less amount of gas, which helium is expensive today, so that's a good thing. It doesn't have a parachute like the normal drop sound, and we also, in fact, have a release mechanism, so we can drop it from a given altitude. If it's going up with a weather balloons, you can drop it from, let's say, 5 kilometers, and then it makes a different profile coming down as a drop sound.
Kim, we're still on your first slide. I don't know if you mean to be advancing that, but we're still on the first one. So.
Oh, you are?
Yes.
Don't you see? Huh. What do
it's
you
a
see
nice
now?
slide, but I know you have more there.
I'm now on page 3. Don't you see it? May I?
Strange.
If I go out of this, good that you mentioned. Let's see if I can escape this one. Use it now?
No, still, now we see we see the third slide now. Yep.
Okay, sorry for that. Great. Yeah, I talked you through the benefits and all the other sensors we have. I think I need to go with this mode.
Okay.
Let's take the next one. Where do I get it? Here. Of course, when you have a sound, you have a complete sounding system. So in the case of a radio sound, it goes up with a balloon. We have a steerable antenna. And in case of a drop sound, we use the antenna on the P3, which is readily available. And then two sorts of receivers. The Stream RX8 small box handle 8 sounds simultaneously, but we're working on a 50-channel version, and I'll be talking a little bit of that later on. And then a post-processing software. But I thought I'd recap a little bit of the history and evolution of wind measurements in general. So as I mentioned, the only global system before 1995 was like Omega, and it was to be discontinued. There was discussion about discontinuing it in the early 90s, so we really had to find a replacement, global replacement, and GPS was the way to go. Accuracies in Omega, really bad, like 10 meters per second and a kilometer of accuracy. Lorentz is a little bit better, but that's regional, that's not global, and it's not really utilized today in any radio drop zones. That was a little bit better in terms of velocity and positioning accuracy. But what really was a game changer in '96 was when GPS was introduced. So we could achieve a velocity measurement accuracy of 0.5 meter per second and a position accuracy of 2.5, so a factor of 10. But at that time, GPS was the only available constellation. So the number of visible satellites were quite limited at that time. But now, last year, we introduced a GNSS version. So GNSS stands for Global Navigation Satellite System, and it's not only GPS, it's also Galileo, the European system, Beidou, the Chinese, and Japanese quasi-Zenit. I left out GLONASS, the Russian system, because of political reasons. We could use that as well, but that was another game changer. So going from single band GPS to multi-band GNSS, you have another factor of 2.5 improvement in both velocity and position accuracy. So again, not as big a step as in 96, but indeed an improvement. So what we did, we were in our first mission 3 weeks ago, we flew into Hurricane Nigel. And one of the experiments, we dropped 8 of these stream sondes in a rapid succession, so like 10, 15 seconds apart. And we have a 3D animation that really shows how the sondes come down. They're flying differently with different velocities. And Josh, as we speak, is analyzing the data. But our point is that scientists can get additional valuable in situ measurements not seen before. And the targets for next hurricane season is to have the stream sondes in operational deployment and release the 50-channel radio, so that enables a true swarm measurement capability. I've always said we should throw out a bag of these from an aircraft, but that might be difficult to do in practice, how to get out such a big number of sondes simultaneously. There's one tube that can feed the sondes out, but that's it. I know the C-130, you could open up the back hatch and throw out the bag. That might be a little bit scary, I guess, in a hurricane. And then finally, so Josh and his team are now analyzing the data, and here's a comparison. I took a plot from you, Josh, so showing different types of winds. I mean, we show unfiltered dual band GNSS wind data versus a normal drop sonde, which is single band GPS, and they indeed show difference, but we are actually measuring the truth, so you can debate what is the wind. But that's for the scientists to figure out. Thanks, that was my few slides.
Tim, that's a great presentation. I wanted to ask you, when these sondes are collecting data, where are they transmitting that to first? Are they transmitting that, is that through satellite, or are they transmitting back to the plane?
Back to the plane, like the normal drop sondes. So the link budget for our half-an-ounce sonde is like, it's 100 miles at least, so 160 kilometers.
Tim, I also wanted to ask you, when you have a swarm of these, I'd imagine you're getting really like a high density of a lot of data in a small area. What's the advantage of that? How can meteorologists use that to better forecast hurricanes?
I think you need to address that question to Josh. I'm not a scientist per se, but I believe the more data, the more beneficial. You can do a lot of new stuff and analyze different things about the motion and the turbulence and what's going on a small level of detail. So I think Josh is better to answer
Kim,
those.
can you unshare your screen?
Oh yes, sorry, stop sharing. Thank you.
Thanks. Bill, Tim, any follow-up questions?
Yeah, I'm writing them down faster than I can think. This is fascinating. From talking with the scientists that are on the planes and on the ground that use this data, do they see this as a augmentation to the current drop sonde, or a replacement eventually?
I would say it's a complementary. So it's the classical radio drop sondes will not go away, I'm sure of that, but this is sort of complementary additional data, and you get another view, more data, but different.
Yeah, I was a little intrigued by the graph you show, the comparison. That at first it looked like a big difference, and I realized that it was only a meter per second each tick mark. So there really isn't that much different. But what could explain that in general it looked like your new sonde is a little bit showing a little bit less velocity than the filtered sonde. In my quick thinking, I thought it would have been the other way around.
That was my initial thinking as well, but I'm not that familiar with the current drop zone, but I believe there's some motion black magic stuff to compensate that it doesn't fall truly it doesn't follow the sort of natural winds. So how do you call it? I think there's some algorithms that does some tricks because the mechanics, it weighs so much more and comes down like a bullet. So there's some black box magic that I'm not aware of. So we just present the raw data as is, and it's doing these small scale movements. And you can see it from the 3D motion sensor as well. So it's coming mainly with the nose down, but then it's doing sort of following the winds as it flies. So that's for the scientists to figure out what's really going on. And I'm excited to. Yeah.
As far as receiving the signal from them, how far away can the plane get before it loses a signal?
Well, the theoretical link budget is about 150 miles, but in the P3, the plane unfortunately has not an optimal antenna, and there's an old filter amplifier which has a really bad noise figure. So with the current P3 setup, we're good to about 100 miles. But if we are in the phase of upgrading the P3 antenna part, so then we can get an additional 50 miles easily.
Yeah, that's great. The standard routes that there are flight patterns they take rarely get beyond that on it. So how long do they stay aloft and keep reporting?
These were like 6 minutes, if I don't remember wrongly. So double the time as a normal drop sonde.
Okay, so they're not going to outrun the signal then, the way it's currently working.
No.
I know they probably cost a lot now in an experiment mode, but if you scaled it up toward using them operational, would the cost be somewhat reasonable? if I'm not sure how to define reasonable when you're trying.
Yeah. I know your. So less than half of what current drop zones cost.
Okay. Boy, I see a lot of things for that. Okay, Tim, what we got coming in on the line there?
Yeah, a couple of questions. One, you talked about operationally perhaps next year where you got your radio receiver can handle up to 50 at a time. Do you anticipate trying to do that 50 multiple times during a storm? The mass drop of even you're probably not going to open the back of the plane and drop them out, not yet at least, but not if Bill's on the plane.
Well, Joe has been talking in practice could be like 20 sondes in a batch. So like 10 seconds apart, 20 of them, and then do another drop of 20 later on. But at least the receiver can handle 50 simultaneous channels. So.
And another question came in from online with the reduced weight. How much extra time collecting data does this take compared to a standard drop zone in terms of time in collecting the data?
I think it's instantaneous, so no difference.
Go ahead, Bill.
Yeah, while we're on that kind of thing on that many sensors, Joshua, you might have some insight as to what you're going to be looking at with that many sensors. What are you looking for in that data to forward our understanding of the hurricane? That question was aimed at you, Joshua.
He may not be able to hear you.
I think we might be.
My computer froze if you can hear me.
We got you, yes.
Oh, so I heard the question. So there's a lot of uses for this. So in Nigel, we released 8 stream sondes in a row, and we can really get the structure of the eye wall for the first time, the very small scale structures and how that varies as you get closer and farther away from the storm. In terms of launching a lot at once, the idea is to do like parcel trajectories and to see where the air is going. And so let's say you have an air mass that's very favorable for intensification of the storm, we want to know where that's coming from and if that is going to influence the eye wall. And so effectively, we think of it like Dorothy, like the movie Twister, where you release a swarm of these instruments and see where they end up and take measurements everywhere.
Wow. Do you think with the large number of these, you might capture some of the structure of the vortices we sometimes see in the eye walls?
Oh, absolutely. And I think we did capture that in Nigel. Now, Nigel was a weaker storm, so maybe not the classical vortices, but we started looking at the data from just a couple weeks ago, and I do think you see some microscale structures in there that could be really fascinating to understand.
Fascinating.
I did get another question coming in from Mike, and Mike, you're still there. I appreciate you being here. So we're going to go back just a little bit and bring you back in for a second. And the question actually is coming from Peter Black. You know, Peter. So we're going to go back to the first half hour. But he wants to know how frequently the satellite constellation pass over, for example, the eye of a storm. How often will we see an eye as they go over? So we're going back to that.
Well, with the full constellation, I think we're getting updates on the order of 15 minutes or so. In certain places in the world, not all places, but I think we are pretty concentrated on the global, the tropics and other areas. So I'd say we'd have a path through it, a profile through it once every 15 minutes or so.
I think this is all fascinating. We're seems like we're making some major leaps forward in what we're doing. And Bill, back when you were director of the Hurricane Center, would you have seen all of this stuff, this half-ounce sonde and these drones flying into storms and these brand new satellites and new models? Talk about how things have changed, Bill, since you were in the Hurricane Center.
I'm not surprised. So while I was there were a lot of conferences I'd go to where the cutting edge scientists were explaining what they were going to be working on next and the level of confidence they had that they would get there with this decreasing in size and the different concept for satellites like the constellations. I had never heard of it till I went to a conference, I think in about 2010. And somebody was researching the feasibility of that. So I'm not totally surprised. I'm actually very happy to see it come to fruition.
We just got about 4 minutes left. Hal, let me jump over to you real quickly. We didn't talk about GeoTrek today, so let me get your GeoTrek update, and then we'll have some final thoughts from everybody before we wrap this up.
Yeah, Tim, a super quick GeoTrek update. GeoTrek travels the world looking for stories related to extreme weather and natural disasters not covered by the mainstream media. You are absolutely going to want to check out next week's podcast that's going to air on Tuesday. We're going to look back at Hurricane Ian 1 year later with Matt DeVitt. He's a weather personality from Southwest Florida. Also, Casper and Kylie Gregory from the Tropical Weather Threat Society are going to be with us. We love going into storms and documenting what's happening in real time, but it's also really interesting to look back at a big time hurricane impact a year later, see what's going on in the recovery and what we can learn from that about how to build better and mitigate losses for hurricanes moving into the future. Thanks a lot, Tim.
Perfect. Thank you for that. Those are always such great programs. We appreciate that. And we know that Casper and Kylie are regulars on this program. So we appreciate them being here. All some great questions coming from them. So I'm looking forward to that. Let's go back to Kim for some final thoughts. We're at about 2 minutes till the end of the program. Kim, a lot of great things happening, going operational hopefully next year. What do you see in the future? Where are we headed?
Well, I hope to keep doing instruments for the coming next 20 years and come up with some fancy technology. I mean, we're also working on GNSS metrology, and it's doing not radio occultation, but doing GNSS measurements with a large network from the ground and doing slant delays and to get a different view of how the atmosphere is constructed. So they will use our dual band receivers, but different than the Spire is. We're doing from the ground, whereas they are doing it with the satellite with a different angle. So I think that's the next project I'm working on.
Can't wait to see it. Bill, in 15 years, we'll be having this conversation. We'll say we heard it on NTWC Live back in 2023. So great stuff, Kim. Thank you so much. We appreciate that. Let's see. Mike, you're still up there. Talk about where you guys are headed from here. A lot of big improvements already. And where are we headed?
Well, we're launching more and different kinds of satellites, hyperspectral, microwave, so we can get better soundings. We can actually see the moisture in the atmosphere far better. It's like a radar from space at that point. So it's just And then you get more and more satellites up too, right? We're launching, 9 or 10 at a time, and so all of that. But then I think the key part is, how do you turn that into something that really creates value for people, right? Better forecasts of hurricanes, better forecasts of winter storms, all that is the key part of it. And so it's the whole value chain that we're trying to create at Aspire, to become a global supply chain and logistics solution provider, if you will, is ultimately where we're going.
Great data. Anxious to find a way to tap into it and see what's going on. So we appreciate that. Thank you, Mike. Appreciate it. Hal, what did we learn today?
And I learned so much. Like Bill said, I can't even really get it all on one sheet of paper. It was just great to see how all these technologies are working, hear from these experts. And I just learned a lot about how really the data collection and getting out there, these different sensors and technologies are improving. And it's amazing to see how small a lot of these have become over time.
Awesome. And Bill, what's your takeaway?
Some of the holy grail stuff on data assimilation and initialization of models on a scale that we can capture some of the intensity factors of storms that have been so elusive. I think we're getting there.
And I think Dr. Josh is gone. I would ask for a final comment there, but I think he's disappeared. But thanks to him for all he's doing at Embry-Riddle. We've had some good broadcast meteorologists come out of Embry-Riddle that we've had at in our shop the last few years. So we appreciate all they're doing there, not just for broadcasters, but for everybody. That pretty much wraps it up. Great program today. Thanks to our guests who've all been with us. We sincerely appreciate it. Want to thank our sponsors who are part of this program week in and week out: USAA, South Padre Island Convention and Visitors Bureau, the Weather Company, and Weather Boy, all a big part of this program. Not only NTWC Live, but the National Tropical Weather Conference itself in South Padre Island. We'll be back there in April. We hope you can join us there. And of course, the Storm Science Network, the things we do with that. We appreciate that. Thanks to all the viewers who are with us today. Next week, we're going to talk about meteorology, MEDIAR, meteorology, and how forecasts can go wrong. Matthew Capucci will be with us, Ed Petrowski, and Will Henderson, all part of the program next week. So that's next Wednesday at 10 a.m. In the meantime, have a great week. We'll see you next time. Take care. Bye-bye.
Bye.
We hope you enjoyed this episode of NTWC Live Hurricane Center Podcast. If you did, head over to Apple Podcasts and leave us a 5-star review. And join us next week. This is NTWC Live.